This playlist combines the modules of our first lecture on propositional logic, a deductive logic that has an underlying structure that relates simple statements together in terms of their truth values in order to determine validity or invalidity of arguments. So we're going to start off this lecture by talking about the elements that all formal systems have, the three elements every formal system has. On one hand, there's the formal system itself, a symbol system or set of representations. Logicians usually call it a language that takes an argument in a native tongue in a situation and translates it to make the underlying structural relationships explicit. So our formal system for propositional logic is going to translate propositional arguments so that the underlying structural relationships between the truth values of individual statements are now rendered explicit and available to us when normally they are opaque and not necessarily easily accessible for us. Second element of a formal system is called an effective decision procedure or a decision procedure. Decision procedures are methods or techniques that take that new information that's made explicit in the formal system and use it to evaluate or formulate an argument, an inference, or a decision in a way that optimizes the goal of that kind of argument, inference, or decision. Finally, there's translation heuristics. As we'll see, in order to get an easy to learn, workable system that's as powerful as possible and has as good a decision procedure as possible, trade-offs have to be made, and the price that we pay for those trade-offs is translating complex variable situations in the world or arguments in language into our much simpler formal system. So translation heuristics are the things that take our problems, our arguments, our inferences, and put them into the formal system. So this is Carl Hempel. Carl Hempel was a logical empiricist. I'm going to use him as the mouthpiece for the view that I'm going to articulate on formal systems. So one creates a logical system in order to make that implicit logical structure of some class of arguments or inferences or decisions, make that structure explicit. That is to formalize it so that you can evaluate the logical form of the argument. And you can do so in a way that is free of those potential biases of content and context that we have observed so often in discussing arguments up to this point. Now, this formalization of a class of arguments or inferences or decisions involves these three elements. First, we're going to create an explicit representational system, that is a language or a symbol system, that makes the important logical structure of the argument class explicit. I call this a formal system. It's sometimes called a symbol system, sometimes called a language. So for example, one that you're more familiar with, numerals symbolize quantities in mathematics, and symbols like plus or equal symbolize operations and relationships. The second element of our formal system is a decision procedure. When we render the logical form of some argument, inference, or decision explicit, the problem with that information is it's now available to us, right? But it's not available to us in a way that's easily utilized for us. We remember when we looked at abstract versions of arguments, we discovered they were harder to evaluate than arguments where the content was explicitly available to us and indicated the underlying relationships. When you abstract away from content, you make it harder. And so decision procedures are introduced to fill that void and to do so in as systematic and complete a way as possible. You have to find techniques, methods to evaluate the logical structure of a given class of arguments or inferences or decisions so that the user now can decide if any argument has good logical form. In most deductive logics, the decision procedure is effective because it's going to tell you for all such arguments, any instance of that argument class, whether or not that instance is valid or invalid. It's effective because it always gives you an answer. The answer is always correct. Now, logicians and mathematicians prize effective decision procedures for obvious reasons. Those procedures are always going to give you a solution. The solution is always going to be correct. As long as you follow the rules, you get your answer. Unfortunately, as we'll see when we get into probability theory, for example, not all decision procedures are effective. So for instance, our counterexample technique from the arguments chapter, that could show that arguments were invalid, but it could only show that arguments were invalid. It couldn't show that they were valid, and it could only show these arguments to be invalid if we discovered a substitution instance that revealed the premises to be clearly and obviously true and the conclusion to be clearly and obviously false. Likewise, in most areas of mathematics, we only have solution procedures. We don't have effective decision procedures. In addition to making this underlying logical structure explicit, one formalizes a given class of arguments with two real goals in mind. First, one wants to capture all of the arguments of that class in one's formalization. You want power. Second, you also want to make your formalization as simple to learn and as easy to use as possible. So you want speed, you want tractability. As I've noted repeatedly throughout the term, these two goals are somewhat orthogonal to each other. They aren't always satisfiable. In fact, most times they aren't satisfiable simultaneously. So one tries to balance completeness or power against ease of learning and ease of use. Thus, one creates an artificial and simplified system that represents the logical structure of that class of arguments or inferences or decisions for which one has an effective decision procedure, at least in deductive logic. One rigorously specifies these elements in one's logic. So we have a simple system. It's easy to learn, it's easy to use. We try to maximize its power. But here's the rub. To pay for that trade-off between power and speed or ease of use, you have to make up for that with your translation heuristic. You have to take the much more complicated world or set of linguistic arguments or your inferences or your decisions, all these complicated nuanced cases, and you have to cram them in to this simple system as best you can so that you maximize your investment in creating that system so that you can use it for the most number of cases possible. So you have to find a general but fallible set of strategies for taking these more complex arguments and inferences in your target class there of arguments and inferences and adequately representing their logical form in this much more simplified formal system. So for instance, in mathematics, we translate by counting and measuring objects. And this works pretty well, unless we mismeasure, unless we miscount, or in some cases, we have to change or fudge or move around in order to get things right. So for example, if I took a drop of mercury and I put it in a pan, I'd have one drop. I put another drop into the pan, I have one drop. I put another drop into the pan, I have one drop. So I have to change my number system by changing my units from drops, say, to volume or to ounces or even mass.